Yeah, we're good, right?
Okay, so,
Yeah.
Oh, I made it up. That's why I didn't do this.
so here's what you got on that rate limiting step. And this is kind of manifestation of what you're gonna see in the lab today. So, this process that you're doing in number one is what you're gonna do in the lab for the next couple of days. You're gonna come in and you're gonna say, okay, in the lab today, you're gonna have 3 different reactants. You're gonna have iodine, you're gonna have acetone, and you're gonna have hydrochloric acid. Okay, so those are your 3 reactants. Now, and this is where you have to understand this concept that not everything happens in one elementary step. So, even if you look at the reaction, and I'll go through this later, iodine and the acetone react and you actually get hydronium ions as a product. So if this was an elementary reaction, there wouldn't be much point because you know it could only be dependent upon the concentration of the iodine and the concentration of the acetone. You wouldn't think the hydronium ion concentration would make any difference because of the fact that that's a product. Doesn't make sense. Well, in reality, it does. And so what happens, without going with the short version of this, we'll talk more about it later. But the short version is there's a slow step, okay? This is like a 3-step reaction mechanism in reality. We write it as one big reaction. In reality, there's 3 different intermediate reactions that take place. And there's a slow step where you produce hydronium ions. And then those hydronium ions gets consumed later on, and then in the overall reaction it appears as a product. So the reason that the hydronium ions are a factor is because in this mechanism, hydronium ions are involved in the slow step. So the reaction, and here's your overarching theme, is that your reaction can't go faster than the slowest step, okay? So it would be like, imagine this, you're on the playground, and you've got 5 kids running across the field. And the teacher says, hey, y'all can't have Skittles until the last kid crosses the line. Okay, well, no matter how fast 4 kids are, they're eventually world-class sprinters. If you got one kid that says, I think I'm going to stop and pick some daisies along the way. Look, that's kind of cool, right? And he just kind of sojourns along. You know, he could care less because the kid doesn't like ice cream. So no matter how fast the other 4 kids are, they're not going to get ice cream until the last kid crosses the line.
How would they? I thought they were getting Skittles.
Huh?
I thought you said
Skittles, my bad, Skittles. Skittles, okay. Ice cream with Skittles.
Interesting combo.
There you go. That's in common.
I'm willing to.
So, the other thing that you're going to do in this lab is the procedure that you show on step 1, where you pick different concentrations to cancel them out, you keep everything else constant, and you cancel them. So what you should see,
You gotta play about food.
No.
You mentioned that.
out of step 1 is that it's first order with respect to B. Okay? Boom, there you go. Your K value, depending upon if you're working in minutes, which is what this data is in, or seconds, and you put down which one it is. Either that K value is 10 to the -2nd, or is 10 to the -4th, depending upon if you want to leave it in minutes or if you want to change that into seconds. I don't care, but you better tell me which one it is, because 10 to the -2nd is vastly different from 10 to the -4th. Okay, and I'm not going to guess which units that you have. So make sure on that K value that you put the units with it. So on number 4, if you're in hours, okay, that answer should be around 40 hours. Okay? Those are the only ones that are really kind of mathematical. on like 72, you should see that 72 is dependent upon two different concentrations, your hydrogen peroxide and your iodine. So on 72C, you should have two concentrations, your hydrogen peroxide and your iodine. Any questions? That was pretty straightforward. Once, twice,
Oh, how many hours?
Can we go over?
around 40.
I know you said don't make it hard, but can we go over 5? You said don't make it hard.
We can
but
turn
you
this
say
thing over?
not make it hard, confuse me more.
Okay,
Oh, yeah.
that's just a decomposition reaction. So the only thing it can be
even though it's
dependent upon
Yeah.
is the CH3MC.
That is.
That's all you have to write.
Is the second one?
But do we,
I guess it makes,
Oh,
right.
Yeah, that's it. I said,
You
what's
said don't
not
make it
make
hard,
it.
that's hard.
You made it difficult.
Yeah.
I made it difficult
Yeah,
because you told me not to. I'm spiteful.
Oh,
Or like in the,
the actual.
but it still contributes to the rate because
Like it produced confusion.
the reaction still won't occur.
I don't know what you said,
So here's one of my poetic titles.
You were poetic.
Have some at the start and
The exceptional analysis that is oh so fine of the reaction rate of iodine.
You gotta admit, that's the top shelf title.
Top shelf.
Is it as good as Stan Iceberg Bird Camp and the Redox Blue Quartet?
Well, the one that was like 15 pages.
Oh, I forgot about that one. I bet I still have it.
Is it okay?
Huh?
For an hour?
Yeah, that's fine.
That sounds like the title of a book, like a children's book.
Maybe
Oh, that's-
maybe that can be my,
Oh, that's the thing.
Your next book.
This is
or my autobiography.
the exceptional analysis that is oh so fine of the reaction rate of iodine. I like it.
Top shelf.
Pretty top shelf.
Now I got mine.
Yeah, here it is.
Like, I could.
I've got the Redox Blue Baby Jazz Ensemble featuring Stan Iceberg, Basic Blue Bird Camp, and his AT.
I love that
Chemistry
one.
Orchestra.
That's a good one.
Okay.
Do you giggle to yourself when you write those?
Sometimes they scream. It's like that.
I can imagine being like, do I call?
He likes the shoulder. We pay.
That's
others
what I
to
imagine
divide
doing.
this. I think it's
That's probably true.
We pay others to divide this.
No, it's too giddy.
Oh, you're right.
Why would we
I
get
feel
our
like it's not like
own?
not like a speak. It's
Yeah,
like,
you're right, you're right.
When you're right, you're right.
They
I
don't
can't
have that
argue with
skill,
it.
they just have money.
Oh.
We're only good at sports and money can buy skill. Maybe I shouldn't have looked up. Soccer, tennis.
College sport.
This looks exactly
Yeah,
like
DNIL is bowling.
Low-key making some good points. Like, I can't
We're not
argue
good
with
at
it.
football and basketball or everything. It's
But
okay,
what's
we're
the
really bad at
functional group
softball.
CH3?
We,
You put an OH on it, then you
yeah, we were good. We went to state. We
This
were
looks
winning a
like
game
biology.
at state even.
I thought we don't talk biology.
Football, no, we were not good.
What's this?
I'm skipping bio today.
Yeah, for a little bit. Problem is, like, if I hear kids speak my language, I have 6 years every year, and we just kind of fall.
Well, first,
They were fun.
Probably.
Okay,
I mean, I substitute.
Kevin, are we still going?
yes, we are.
Okay. All right, so there's gonna be three distinct parts to this lab, okay? One is figuring out the order of mechanism, then once you figure that out, predicting a rate of the reaction. And then the third one is determining the activation energy for the reaction, okay? So this is why this lab kind of takes 3 days to get done. So here's the basic idea. Is that you're going to take acetone, which, and don't worry about the chemical structure of it, it's just acetone, okay? if you've ever worn nail polish and tried to take it off, you've used acetone. It's 4 mole, it's fairly concentrated, acetone's flammable, no smoking in the lab.
Dang it.
I know, shocking. So then,
Can't have anything.
you're gonna react with iodine. Now, this is elemental iodine, this is gonna be important. This is elemental iodine, but it's suspended in basically a water solution. So it has a distinctive brown color to it. So as long as iodine is available in the solution, you can see it. As soon as the iodine is used up, the solution goes clear. So we're going to take advantage of that because we can't directly measure the iodine concentration. We could, but we'd have to use a spectrometer, which we will deal with later. But it's a simple thing. So basically what we're going to do is we're going to say, okay, we're going to start this reaction with the acetone and the iodine. And you're going to time it. As soon as you add the iodine, boom, you start it. Then you're going to stare at it, and you're going to watch it until the solution goes clear. And when the solution goes clear, the reaction is used up, boom, stop the stopwatch. Now, this is what I was saying. Here's your overall reaction. So basically what happens is this. You take the elemental iodine and you split it apart, because it's iodine, it's elemental, it's the elemental form. So you have to break the bonds that hold the iodine together, okay? So this is where, like in activation energy, and we'll talk a lot more about activation energy. So if you look at energy versus time, so what you have to do to get the party started is that you have to invest some energy. You have to invest some energy to break the bonds that hold the iodine together. You also have to come in here to the CH3 group, and you're going to break a bond between the carbon and the hydrogen. So you're going to break 2 bonds. You're going to break the iodine bond, and then you're going to break the bond that holds the carbon to one of the hydrogens. Then the iodine, one of the ones that are free, basically comes along and says, yo, sup, okay? Mind if I dance with your date? With prom coming up, that's a relevant analysis. So the hydrogen leaves to go get his picture taken, the iodine slides in, says, yo, let's dance. The other iodine, though, is upset. So it's left out going, hey, yo, you know, you brought me to the dance and you're over dancing with the CH3s and I'm off by myself. And like, well, sorry. But then you also have some hydronium ions that are left over as well. Now, what will the hydroniums and the iodines hook up to make hydroiodic acid?
No.
Strong acid.
Strong acid. Okay, it's not going to get
Clumpy.
clumpy, okay, because they don't like each other. They're attracted because we're opposite the charge, but we're just friends. So they're not going to get clumpy, all right? So this is going to take its place. So if this is the classic example. If this is all you saw, you would not think the concentration of the hydrochloric acid would make any difference, because of the fact that the hydronium ions are showing up as a product. You would think, oh, okay, great. We only have to worry about the acetone and we have to worry about the iodine and that's it, okay? Don't have to worry about the hydronium. It's there, we really don't need it. But in reality, and this is what you'll see, is that it is dependent upon the concentration of those hydronium ions, which tells you that this is not an elementary reaction. If it was an elementary reaction, we wouldn't have to worry about the concentration of the hydronium ions. This means that there's actually like a 3-step mechanism to explain how this works. Okay. So got the idea. All right. So over on page 4, okay, you've got, this is going to be the heart and soul of this entire lab, okay, is these charts. So let's focus on this chart kind of right here in the middle. So listen to me very, 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 very carefully. There's certain techniques you need for this lab. So you need a couple of people that are gonna make observations. You need 4 identical test tubes. 2 of them you're going to fill with water, okay? That's gonna serve as like the control, okay? Deionized water, put it in, fill it up about halfway. Then, so like, let's say 1G and I are gonna be doing this. So you're gonna have a set of these, I'm gonna have a set of these. One of yours is gonna be water, one of mine is gonna be water. Then, it says to use an Erlenmeyer flask, it really doesn't make any difference what you use. You're gonna mix together some iodine and the acetone, okay? You can mix that together anytime that you want. You're gonna measure it out. You're gonna measure out very, 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 very specific quantities of these things. This isn't add about 5 milliliters. No, this needs to be very, very precise measurements of these quantities. And then you're also gonna add some water. We add the water so that the total volume in every reaction remains the same, okay? So you're gonna add some water. So you're gonna get all of that ready to go. You're gonna add the water, the iodine, and the acetone. The reaction is not going to start, okay? Because you haven't added the magic ingredient of the hydrochloric acid. It really doesn't make any difference which one you add, but let's add the hydrochloric acid last. So then, what you're gonna have is then you're gonna have the container that has the hydrochloric acid. So as soon as that gets added, give that a swirl. That's gonna start the reaction, okay? Boom, the reaction started. Now at this point, here's what we're gonna do. At that point, you add that, start your stopwatches. Ideally, I'd have one, 1G would have one, okay? We would be independent, like you do you on that side, I'm gonna do me on that side, okay? Hit start, boom, same time, okay? Not when you pour them into the or when you pour them into the test tubes, but when you mix everything together. Then what's going to happen is that 1G is going to look down her test tube, I'm going to look down mine. And we're going to watch these. And we're each going to stop it when these test tubes that have the iodine become clear, okay? Now, obviously that's kind of a judgment call. It's like, but it's handy if you hold it against like a white paper. That makes it easier to see than if you hold it against the lab table, because the lab tables are black. And sometimes it's hard to see that differentiation. So then in an ideal world, I see mine, boom, I stop mine. I don't tell 1G when I stop, because I don't want her to be biased, okay? So then she's gonna run hers, she's gonna stop hers when hers goes through. Hopefully, they agree within about 20 seconds of each other. Okay? Now, if they're off by like 5 minutes, something has gone bad, right? Something has gone very, very bad. So, what you're going to do here is that up here on the top, it's going to tell you the volumes that you're going to mix together. 10 milliliters of the 4 molar acetone, 10 milliliters of the iodine, 10 milliliters of the hydrochloric acid, 20 milliliters of the water. So I'm going to record my time, 1G is going to record her time, we're going to take the average of the two. Now, only do that if the times are relatively close. If the times are off by 5 minutes, don't take the average. Something is completely jacked up. So, like when I did it, mine took me about 3 minutes, okay? That's kind of a ballpark so you get an idea of how long. Don't think, oh, this is not like the explosion of hydrogen and oxygen where you go, start, stop, okay? The reason that we do this particular reaction is that it takes a while for this reaction to run. So don't think, oh, as soon as we add it, it's going to change like within 5 seconds, okay? It's going to take a while, all right? And you don't have to sit there and go, stare at the entire time. You'll see it begin to fade. Okay, and as it begins to fade, then you really need to begin to pay attention to that time. Okay, now let's move down to this column where it has like mixtures 1, 2, 3, and 4. So I want to make sure everybody's cool with how you fill in this chart. So listen to me, listen to me, listen to me. These are the concentrations of these reactants after they have been mixed, okay? It is not the stock solutions coming out of the reagent bottles. This is after they have been mixed. So what we're going to use is M1V1 equals M2V2. Okay, so just if you've never seen this, this is what you use for dilution concentrations. Okay? So what you're going to do is you're going to mix together, and I'm just showing you where these come from. So you're going to mix together 4 molar solution of your acetone. That's what's going to come out of the stock solution. What I would recommend, because you've got iodine, 4 molar hydrochloric acid, and 1 molar hydrochloric acid. The iodine will stain your clothes, don't get it on anything, okay? Just saying, even though it's diluted, it will still stain your clothes. If you get it on your paper, don't flip out. If your paper turns purple, it reacts with the starch in the paper. Okay, so there's a little biology, okay? Little iodine and starch happening. Just chill out and go kill the messenger. So what I would recommend is that maybe you, instead of walking up every time, just get about 50 milliliters of each one to start, and then you just draw from them. Just make sure they're labeled so everybody knows what they are. Okay, so on the first one, you're going to mix 10 milliliters of this stuff. Okay, this needs to be exactly 10. Okay. This is not, it's about, no, this needs to be exactly 10. Now, if you look at this, the total volume of the acetone, the iodine, and the hydrochloric acid, and the water adds up to what?
50 milliliters.
50.
Yes.
So I'm going to have a new molarity that I don't know, and 50 milliliters. Go, good luck. Although we're not going to get anywhere near being done with this lab, so you can just catch up tomorrow. So if you take 4 times 10, you get 40. Divide that by 50, you get 0.8 molar solution of your acetone. So that's where that 0.8 came from, okay? So it isn't just, oh, it's just magic, okay? That's where that came from. So you're going to do the same thing with the iodine. Oh, you're going to mix together 10 milliliters of a 0.0050 molar solution of iodine, which is going to equal 50 milliliters times some new molarity. So what's going to be common on all of these is that you're always going to end up with a total volume of 50 milliliters. Okay? So on trials 1, 2, 3, and 4, you're going to end up with a total volume of 50 milliliters. Okay? So, now, here is where the magic is going to happen. To calculate the rate, here's what we're going to do. This is down there on that middle column on page 4, where it's going to rate equals your I2 concentration initial divided by your average time. So here's what you're going to do. If you look on this, and the reason that we use the iodine is because that's the one that we can measure. So if you do the stoic on this, what you'll see is that there's heaps and heaps and heaps of acetone. There's heaps and heaps of hydrochloric acid. So we're going to run this so that the Leamington reactant is the iodine. So basically, as soon as the iodine is used up, we assume that the reaction is going to stop. So the iodine is the limiting reactant, because that's the only way this works. If the iodine isn't the limiting reactant, like if we have the hydrochloric acid being the limiting reactant, and the reaction stops when it's used up, well, that's cool, but we can't tell anything different because the hydrochloric acid is clear. This is why we let the iodine run out first. Okay, does that make sense? All right? Okay. So, you're gonna know the initial concentration of the iodine, which in this case, if you do the math on trial 1, that's 0.0010 molar. That's the initial concentration of the iodine. When it gets done, what's the final concentration of the iodine gonna be? Do not make this difficult.
0.
0. Now, you're going to divide that by the average time. So this is what we're going to use to get the rate, okay? So we could use a rate, either the rate at which a reactant disappears or the rate at which a product appears. Well, your two products, or the three products out of this thing, don't have any color. So the only thing we can do is base it upon the rate at which one of the reactants is consumed. Now, conveniently in this reaction, everything is in a 1-to-1 ratio. So we don't have to worry about stoic. It isn't like, oh, we're producing 5 moles of iodine or something like that, okay? It's not what we're doing. So in that regard, it's pretty simple because of the fact that the stoic is simple. That's why we do this. So, to give you a hint, okay, that rate on mixture 1 typically is around 10 to the negative 6th, okay? Typically around 10 to the negative 6th. It's ballpark, okay? If you get 10 to the negative 3rd, something has gone horribly wrong, okay? And like I said, when I did it, it took about 3 minutes. So again, just don't think this is going to happen very, very quickly. This is not the most exciting lab you're ever going to do in chemistry. It's like, what are you doing? Watch an iodine disappear. That's fine. Woo!
What?
Yes!
AP chemistry.
Yes, what'd you do? Watch iodine.
We
Like,
should have done
Turn
that.
from
it's
round to
just
clear.
like,
We should have
that's
done
what I
that with
thought.
the elementary
I didn't know if you
kids.
made it.
Yes.
Just be like, it's gonna take a second.
Give it 3
yeah,
minutes.
just give it 3 minutes. No,
It's brown,
Or-
not pink.
that would be bad.
Put on some cocoa
What?
melon.
Is our
That'll
temp
be fine.
just the temperature of the room?
No, it's gonna be the room temperature of the solution.
Oh.
Yeah. The only temperature that you're gonna need is like the temperature after you mix everything together. Later on, we'll change the temperature. Okay, but your temperature is just gonna
Is that
be,
part?
This is sounding like.
yeah, that's gonna be part 3. Okay, so here's the big picture. You're gonna run 4 different reactions. Whether you change, and all of them, you're either gonna change the iodine concentration, the acetone concentration, or the hydrochloric acid concentration. So you got 3 variables. So here's gonna be the big picture. What you're gonna do is you're gonna try and find the order of magnitude relating to this reaction. So what you're eventually gonna do, so here's the big picture, okay? Your big picture is eventually you're gonna try and find the order of magnitude of, say, the acetone. So you're gonna sit there and go, okay. So your rate is gonna be the concentration of your acetone to the X, and I tell you exactly how this is going to play out. So up there, kind of in the middle of page 4, you've got acetone to the X, iodine to the Y, and hydronium ions to the Z power. So what you're going to do, eventually, you can't do this obviously until you get all your data, which you can't do until tomorrow, so no, you don't have any homework tomorrow. So eventually what you're going to do is you're going to pick reactions and you're going to isolate variables. You can say, okay, hey, I want to keep everything the same, and I'm going to look at how the impact of the hydronium ions. Or I'm going to isolate them and make everything cancel out with the iodines, or everything cancel out except for the acid. So what makes this a little bit more complicated, you guys are used to doing this with 2 things. This has 3, okay? So don't flip out. It's not that big a deal. It's the exact same process. And I'm going to restate this again tomorrow. This is a very formal lab write-up. when you do this and you write these out, I want to see, hey, these are the reactions that I chose. Here's my concentrations that are cancel out. Here's my order. Now, here's the other thing that happens because you're actually dealing with real data. Sometimes you might have to get a little creative with the rounding, okay? I'm just saying. So, in theory, I know what should happen, okay? And generally, it does, okay? 95% of the time, this lab pretty much goes like it should. Every once in a while, and this is something Kevin brought up, and that is related to temperature. This reaction is exceptionally temperature dependent, okay? So the temperature changes a little bit, that greatly affects your rate. So when you do this, don't hold the ones that have the iodine in them, and do not hold them in your hands, because what's the solution going to do? Warm up. So if 1G is holding the test tube and I'm not, her rate's going to be much faster because she's adding thermal energy into that, okay? So I would suggest you hold the test tube up towards the top, like on that rim, so that you're not adding any thermal energy into that solution, okay? So if today we can get through maybe the first, second, maybe the third reaction, that would be cool. When you get done, you can wash everything down the sink, label everything, okay? Because these all look the same. The acetone will look a little bit cloudy. Don't flip out and go, oh my God, the acetone's cloudy. It's okay, it just has a little bit of cloud to it. Okay, are you ready? Great. Kevin, stop.